Hi, welcome back everybody. Today we're doing section 14.3 where we're going to be talking about partial derivatives. Now, when we look at partial derivatives, we're going to have to go back to what we learned back in Calc 1. So here, what I'm going to say is from Calc 1, and let me actually reduce the pencil here. There we go. All right, so from Calc 1, we were able to extract that if we were looking at a derivative of a function, then we had this limit definition, limit as h is approaching 0, for f of x plus h minus f of x, all divided by h. Provided that the limit exists for this function here, we would be able to extract the derivative of that function. Now, the reason why I want to call that into view is because when we start dissecting certain functions here, let's say we had a function f of xy is equal to cosine of x plus y. Then here we have this function where the domain is all the ordered pairs in the x and y coordinate system. Now, the question then becomes, can we find the rate of change at the point 0, 0. All right, so that's the question here. Now, when we're looking at this, we then have to say, okay, well, we're dealing with a multivariable function. In other words, we have this function that has both x's and y's embedded into it. So what we're going to do is we're going to take an approach and we're going to say, all right, you know what, yes, we can do this, but one thing that we need to do first is we need to fix a coordinate. All right, so first, we're going to fix x is equal to 0. And we're going to do x is equal to 0 specifically because we have an x is equal to 0 on this coordinate here in the x's and y's. All right, so since we have this, let's go ahead and let's follow through. Now this becomes f of 0 comma y is equal to cosine of 0 plus y, which then just turns into cosine of y. Now, looking at this function, this is going to give us something beneficial then. All right. Now, I've gone ahead and I've taken the liberty to put this on GeoGebra, so we're going to look at this on GeoGebra really quickly. All right, so here's GeoGebra. Here's our function. Whoa, where'd it go? There we go. There's our function here. All right. So here's our function. Now, what I want to do is I want to identify the point 0, 0. All right, now the point 0, 0 in the x and y coordinate system would be somewhere around here, somewhere around the origin. All right, now I tried my best to get it exactly at the origin, and that's the best I can do right here. So for the purposes of this problem, we're going to assume that this ordered pair is already on the x and y being 0, 0, and that means the output would just be 1. All right, so three-dimensional coordinate system, there we are. Nice. Now, since we fixed this, what I want to do then is I want to start observing a certain path on here. Remember, the x coordinate is the one that was fixed. So because x is equal to 0, oops, excuse me there, would you agree that x is equal to 0 is really just this plane? All right. Now, the big question is, when does this plane, or how does this plane intersect this function that we're looking at? And the intersection is this parametric curve. Now, as we're looking at this parametric curve, then we're going to be able to extract, okay, looking at this parametric curve on this specific surface, what is that function? Now, that function, as we start looking at this, let's view in front of, take the guesswork out of that. There we go. Looking at this function here, it kind of looks like it's the cosine function, right? But again, that shouldn't be any surprise because once we were able to fix the point, the x coordinate at 0, we actually were extracting that this is the function that we're looking at, which was cosine of y. Nice. So in this particular case, we have a two-dimensional function. So I'm going to go back to the notes. Now, looking at this function here, I can now take the derivative for this function. But I'm going to call this function really quickly g of y, since it's only a function with one variable. So I can now say that g prime of y is equal to negative sine of y. Nice. And it's at this point in time that I can go through and I can start isolating, or I can start extracting what is that rate of change, right? So if we go back and if we backtrack all of this, then what we really looked at was the derivative for this function with respect to the y variable. The notation for this is as follows. This will be negative sine of 0, because again, we're inputting that y is equal to 0. So y is 0, that means this y was 0. And then from before, remember this 0, x is 0, x is 0. That means x was equal to 0 here. Which means this is our derivative, at least in one direction. Now, it's possible to have more directions for these derivatives. The next direction that we're going to look at is, next, we're going to fix y is equal to 0. And when we fix y is equal to 0, what we have then is this function in terms of x, which means we're going to have cosine of x plus 0, which means this is just cosine of x. Again, it's a it's a one variable function, which means we can call this h of x. Taking the derivative now, h prime of x, would get us negative sine of x. Now, following through on this, well, h was this one variable function, but the one variable function was brought forth by fixing a constant on this two variable function, which means we really took the derivative of our initial function with respect to x. And here, we can say this was evaluated at the point 0, 0 to get this derivative. Now, in general, all right, so let me scroll up here. In general, so in general, f sub prime of y is not equal to f sub prime of x. It is in this particular example because at the point that we're evaluating this at, and simply because we have x plus y in the argument. All right. Now, what does that rate of change look like? So analyzing that rate of change in terms of this given function that we have here, let's stop moving this, there we go. What I want to do is I want to look at these two intersection curves and this point given on the surface. If I were to move this point anywhere on the surface, notice that the curves go along with it. And essentially what I want to do is I want to fix all of these points, x's and y's, at different points in time so that I can take the derivative. If I stop here, then I want to say, okay, what's the x coordinate, what's the y coordinate? Let's fix those values and then take the derivatives independently. That way we can extract what is the overall derivative. But that means that this derivative is then going to travel in some sort of x direction and some sort of y direction. So at this point in time, we can only have two different types of derivatives. We can have a derivative that will focus strictly along the x-axis, parallel to the x-axis, or a derivative that will go along parallel to the y-axis. All right, so two different derivatives that we can look at. Now, given those two derivatives, we can extract a definition that we can work with or that we are going to work with. In this case, anytime that I want to look at the derivative with respect to x for this multivariable function, it's going to be the limit as h is approaching 0 for the function f of x plus h, comma y, minus f of xy. All this divided by h. And if we're looking at the derivative with respect to y, this is going to be f prime of y for this x's and y's for the limit as h is approaching 0 for f of x, comma, y plus h minus f of xy. Now, if you notice, these definitions are very, very similar to the definition that we had from Calc 1. Now, what these definitions, or what these imply here, is that if you want to take the derivative with respect to a certain variable, then you have to treat every other variable as a constant. Exactly like we did in the example above. If we wanted to find the derivative of the function with respect to y, then what we did first is we treated x's as a constant. If we then said, hey, let's find the derivative of the function with respect to x, then that means we had to treat y as the constant. And that's kind of what these definitions are saying here. This definition is only allowing the x's to move, and this definition here is only allowing the y's to move. Therefore, you're calculating the derivative with respect to y on the right-hand side. On the left-hand side of the screen, we're calculating the derivative with respect to x. And this isn't the notation that we want to use. So let's keep on extracting this notation. That way we can start elaborating a little bit more when we're working with these multivariable functions. So the notation for any multivariable function when we're taking derivatives, as you saw, the derivative of the function with respect to x can be written in this manner, or we can just say f sub x. This means that we took the derivative of the function with respect to x. We can take the partial derivative of the function with respect to x. Notice these differentials, they're not exactly the differential letter D. It's more of a different type of letter that we use. All right, still signifying the derivative. Which means here we could be looking at the partial of z. Whoops, excuse me there. The partial of z with respect to x. This could be denoted as z sub x, or derivative sub x using the function f. Now, you're going to see that the very last notation, that capital D sub x of f, we want to use that notation once we get into directional derivatives. And that's going to be in about 2 more sections, or in about next section, about 2 more sections when we start looking at those directional derivatives. Wow, actually 3 more sections in 14.6. All right, so let's look at the next one. Partial with respect to y. Looks almost identical again, but we start looking at these derivatives with respect to the variable y. C sub y and capital D sub y for the function f. There we are. Perfect. Now that we have this notation and now that we have these definitions, let's see if we can go through some examples. So on this example, we're going to find all first order partial derivatives. Now, you're going to see here that using the notation above, if we have a function of 2 variables, then when we take the first order partial derivatives, this is going to imply that we're looking at 2 different derivatives. One, the derivative with respect to x. The other one, the derivative with respect to y. So let's look at this function that we have to begin with. F of xy is given by 2x to the 5th plus 3y to the power of a half minus pi. So let's extract here. We want to take the first order partial derivatives. Now, the first derivative that I'm going to be looking at, I'm going to take the partial with respect to x for this function f of xy, which means I'm taking, again, that partial derivative with respect to x for 2x to the 5th plus 3y to the half minus pi. All right, on the left-hand side, I'm going to use my notation to say, hey, I'm taking the partial of this function with respect to x, so naturally it's going to look like the partial with respect to x for this function f of xy. Now, on the right-hand side is where we now start applying these derivative rules. So applying the same derivatives rules that we worked on from Calc 1, we can take the partial with respect to x for 2x to the 5th plus the partial with respect to x for 3y to the half minus the partial with respect to x for pi. All right, now I'm only doing this to show you how these derivatives are still working with the rules that we have from Calc 1. So for the first term, we're going to take the partial derivative there. So that just means to us, since we do have a variable x, here, all we need to do is just take the derivative that we know how to do from Calc 1. So that's going to be 10x to the 4th. Very nice. Now, the second term, excuse me here. The second term that we need to take the derivative for is 3y to the half. Now, the big aspect about this is that 3y to the 1/2 does not contain a variable of x, and that's what we're taking the derivative for, which means this is now treated as a constant. So the derivative of this function with respect to x, there are no x's, it's a constant, so what's the derivative of a constant? That's right, 0. So this is 0. Pi, third term, is a constant as well, which means that goes to 0. So naturally, then the derivative here, at least the first order derivative with respect to x, becomes 10x to the 4th. Now, we can go through on the second function, Now, we can go through on the second function and do the exact same, and take the exact same approach. The partial with respect to y for this function, f of xy. Let's see, this is going to be the partial with respect to y, and that's going to be 2x to the 5th plus 3y to the power of 1/2 minus pi. So taking that derivative, let's see if we can work through this. Now, the first term, you're going to say, well, Mr. Castro, the first term has an x, it has no y's. You're absolutely right. Therefore, the first term, when we take that derivative, will now become a constant. Derivative of a constant, 0. The only constant that the only term that we really have to worry about is that second term. So let's take that derivative there. Drop the exponent forward and multiply, so that's going to be 3/2. Take the exponent, subtract 1, so that's 1/2 minus 1. It gets us negative 1/2. And then finally, the derivative of a constant, which is the derivative of pi, gets us 0. Naturally, we're at our answer. So when the question asks, find all first order partial derivatives, and we have a multivariable function that has 2 terms, then that means we need to find 2 of those derivatives. Nice. Let's look at part B. All right. Looking at part B, let's see if we can start working this out. Let's see. We're going to have h of x, y, z is equal to x sine y divided by z squared. Now, when we're talking about the first order partial derivatives, since this function has 3 variables, then we need 3 first order partial derivatives. So the first one that we're going to need is going to be the derivative for h with respect to x. Now watch what I'm going to do. Instead of writing all of this out like I was doing before, in my mind I'm just going to envision, since I have sine of y and since I have z squared that both do not contain the variable x, I am only going to take the derivative for the x value. Alright, so I'm only taking the derivative for the x here. Everything else is treated as a constant. So if I treat everything else as a constant, let's take the derivative with respect to x here. That's going to be a 1 multiplied by this variable, or in this case, this constant. Sine of y divided by z squared. That's it. Next one. Derivative with respect to y. So let's go with that derivative with respect to y. So again, treating everything else as a constant. Treat the x's as a constant, treat the z's as a constant. You're only taking the derivative for sine of y. The derivative for sine of y is cosine, which means cosine of y is going to multiply the remaining constants. There we are. Perfect. Now we also need the derivative with respect to z. So the derivative with respect to z at this point in time, again, we're going to treat everything else as a constant. So if z is a constant, or sorry, if z is the function, let's see if I can rewrite this really quickly. This is x sine y multiplied by z to the power of -2. And let's take that derivative with respect to z. So x times sine of y is your constant, so let's take the derivative, drop the exponent forward, that's -2, so this is going to be -2x sine of y divided by, well, we need to subtract another exponent, so it's going to be x z to the power of -3, so that's going to be z to the power of 3. So here are your answers. These are the answers that we need for this variable, or this function, with 3 different variables. Awesome. Now, let's talk about higher order derivatives. All right, so let's look at those higher order partial derivatives. All right, so for these higher order partial derivatives, say that if I had an initial function that I was working with, z is equal to f of x, y, and say that I wanted to take a derivative, first order partial derivative with respect to x. Once I did that, say that I wanted to take another derivative after that with respect to x again. In other words, I took a second derivative, both of these times with respect to x. What this looks like, at least notation-wise, is this. Now, partial derivative-wise, this is going to say that we first took a partial derivative with respect to x here, and then once we were done with this derivative, we wanted to take the partial derivative again for this new function with respect to x. Notation-wise, this looks like partial twice for the function with respect to x both times. How does this look like if we wanted to take a partial derivative? How does this look like if we want to take the partial derivative with respect to x, but then the second time around we want to take it with respect to y? Well, this would look notation-wise f sub x then y. This means that the first derivative that must have been taken was a derivative with respect to x. After that was taken, we need to take the partial derivative with respect to y. Notation-wise, how does that look? This is the partial twice for this function, once with respect to y, then with respect to x. With respect to x must come first, and then after that we do the partial with respect to y. Now, how does it look like when we want to do f double prime of y? Well, this will then look like this notation-wise. Notation-wise, partial of f with respect to y. And that means that the partial derivative was done twice, both times with respect to the variable y. Now for the last option, or the last combination here, we're going to have the partial of y, then the partial of x after that for this function of f. That means the first derivative that was taken, or the first partial derivative that was taken, was with respect to y. Then after that, we need to take the derivative with respect to x. This means that I took two partial derivatives, the last one being with respect to x, but the first one being with respect to y. Alright, now, higher order partial derivatives. As long as we have two variables within the function, we get 4 different partial derivatives. And that's 4 different second order partial derivatives. So as you can see, if we had a function with 2 variables, first order partial derivatives, we need to find 2. Second order partial derivatives, we need to find 4 of them. So this is growing kind of fast, right? So let's see if we can work through this example then. Here goes your example. We want to find all second order partial derivatives. So finding all second order partial derivatives for this given function, and this given function is going to be f of xy is equal to cosine of 2x. There we go, cosine of 2x. Whoa. Cosine of 2x minus x squared e. I don't like the way that e looks. Here we go. E to the power of 5y plus 3y squared. So here's our function. Now we have to take the derivatives. So to start off, or let's go back and dissect really quick. We want to find all second order partial derivatives. That means to us that we need to find 4 of these partial derivatives that are second order. So the first one that I'm going to do here is I'm going to find the partial derivative with respect to x first. So let's go through. For the first term, we got cosine of 2x. Let's take that derivative. So cosine of 2x with respect to x, that's going to cause me to differentiate cosine. That's going to be 2 sine of 2x once I use the chain rule. Good. Next term, minus x squared e to the 5y. E to the 5y is a constant when I'm taking this partial derivative, so I only need to take the derivative for x squared, which will be 2x, so it's minus 2x e to the 5y, then plus 3y squared, but 3y squared, if we're differentiating with respect to x, that's a constant, so the derivative of a constant, 0. Good. Awesome. Now let's see if we can find the partial derivative. Or you know what? Let's actually go through. Let's go to the second order. Now that we found the partial derivative for x, let's find the partial derivative with respect to x again. So partial derivative with respect to x again. First term, take that derivative here. That's going to be negative 4 cosine of 2x minus, that's going to be 2e to the 5y. Perfect. So we got our first derivative, nice, or sorry, our first second order partial derivative. Let's look at the second order partial derivative. All right, we now need to take the derivative of let's highlight this in yellow. Again, the derivative of this function, wow, that is not yellow. There we go. Focusing on this function, taking that derivative with respect to y. First term does not contain a y, that's a constant, so it's going to be 0. Second term that does contain a y, I need to take that derivative. So we now get minus 10x e to the 5y as our second order partial derivative, first with respect to x, then with respect to y. Nice. So now that I have those done, those are two of my answers. Let's see my other answers here. All right, I want to find now the partial with respect to y for this function. Again, I'm only differentiating the y values. First term does not have a y value, therefore that derivative is 0. Second term, I do need to take that derivative, all right, with respect to y. So that's going to be negative 5x squared e to the 5y, once we apply the chain rule, plus 6y. Perfect. Now using this, I'm now going to take the derivative with respect to x. So let's see, taking this derivative with respect to x, or actually let's do it with respect to y. My apologies. With respect to y. Taking this derivative with respect to y for the first term here with respect to y, that means I'm only differentiating e to the 5y. That's going to be negative 25x squared e to the 5y plus 6. Then taking the derivative once again for this function that we're looking at here, we want to take that derivative with respect to x now. So the last term 6y is going to be a constant that goes to 0. The first term here is going to be negative 10x squared e, oh sorry, not x squared, my apologies, 10x e to the 5y. Nice. Now I want you to sit back just for a second. We have our answers. These are the answers that we're looking at. Now I want you to sit back really quickly and I want you to identify what is happening here. Notice that those two partial order derivatives, two second order partial derivatives that are mixed. One was f prime of x, then with y. The other one is f prime with respect to y, then with respect to x. Turns out they turn out to be exactly the same. Well, we do have this one theorem that's going to be very, very nice. This is known as Clairaut's theorem. Now, what Clairaut's theorem tells us that we're going to suppose that f is defined on a disk. Call this disk D. That contains the point AB. If the functions f sub xy and f sub yx are both continuous, on the disk D, then we actually get that f of xy evaluated at AB is equal to f of yx evaluated at AB. Now, what we have to look at here for Clairaut's theorem is basically looking at this function that we were observing on the previous example. We then have to identify, is this function is this function here, or where is this function continuous? Well, cosine of 2x, no restrictions, that's continuous everywhere for the x's. X squared, once again continuous, multiplied by e to the 5y. E to the 5y is again a function that's continuous everywhere for the variables. And then finally 3y squared, continuous everywhere. Therefore, this function f of xy is made up of many functions that are continuous everywhere. Therefore, f of xy must be continuous everywhere. So we can define then by Clairaut's theorem any given disk on this domain, and therefore the partial derivatives, at least the mixed partial derivatives, will always be equal to one another. Alright, so now we're going to verify Clairaut's theorem. So verify Clairaut's theorem for this given function here, which is, f of xy is equal to x times e to the negative x squared y squared. Right. So let's go through and let's start identifying what we need. Now for Clairaut's theorem, we need these partial derivatives. So we're going to go with a partial derivative with respect to x, then with respect to y, so on and so forth. So let's look at the first one with respect to x. So the first partial with respect to x, notice that we are going to have to use product rule. So let's go with the product rule. So let's see. Take the derivative of the first. That's going to be just 1 multiplied by e to the negative x squared y squared. Good. Then plus the first function, which was x, multiplied by the derivative of the second function. So the derivative of the second function, again, we're only looking to take the derivative of e to the negative x squared y squared, and that's only with respect to x. So, taking the derivative with respect to x, that's now going to be negative 2 x y squared e to the negative x squared y squared. Awesome. So that's the derivative with respect to x. Now, let's see if we can clean it up just a little bit more, just because it looks kind of messy here. So let's clean this up just a bit. This is going to be e to the negative x squared y squared minus 2x squared y squared e to the power of negative x squared y squared. Perfect. Alright, so now that we're done taking this partial derivative with respect to x, let's now take this partial derivative with respect to y. So taking this partial derivative now with respect to y. Alright, so the partial derivative with respect to y, for the first term, it's a straightforward derivative. Just take this with respect to y. We're going to have to use the chain rule here. So using the chain rule here, we're going to get negative 2 x squared y e to the power of negative x squared y squared. All right. Now for the second derivative, for the second term, that derivative, we're going to take the derivative of the first here. So taking the derivative of the first function here, we're going to do a minus, and that's going to be 2. I said derivative with respect to y. So here that's going to be 4 x squared y multiplied by the second function e to the negative x squared y squared. There we are. Good so far. Great. Plus the first function, which was negative 2x squared y squared multiplied by the derivative of the second function, the derivative of the second function with respect to y, that's going to be negative 2x squared y multiplied by e to the power of negative x squared y squared. There we are. Now this derivative looks rather, let's say, ugly. So what we'll do is we'll clean it up just a bit. Negative 2x squared y e to the negative x squared y squared minus 4x squared y e to the negative x squared y squared, and that's going to be plus 4 x to the, what is that, x to the fourth, I believe? X to the fourth, y cubed, and that's e to the power of negative x squared, y squared. Nice. Now, if you notice the first two terms are like terms, which means we can condense this into negative 6 x squared y e to the negative x squared y squared, and then plus 4 x to the fourth y cubed e to negative x squared y squared. Nice. Now that we have one of them, again, we're trying to verify Clairaut's theorem, so we're going to have to go with the partial derivative with respect to y. So the partial derivative with respect to y, needless to say, this one's going to be slightly easier because the x variables are treated as constants. So anything that has an x is a constant. Therefore, when we take the derivative here, we should get, let's see, derivative up top over here. That's going to be negative 2, and that's going to be x squared as a constant, so that's going to multiply y squared, so that's going to be x squared times x, that's going to be x cubed. All right, good so far, multiplied by y, and that's e to the power of negative x squared y squared. Nice. There you go, first derivative done. Now, second derivative, we're going to take that derivative with respect to with respect to x now. So taking this derivative with respect to x, let's see if we can pull this off. All right, so we are going to need a product rule here. So product rule, we're going to take the derivative of the first function here. So derivative of the first function, that's going to be negative 6x squared y, and that's going to be multiplied by the second function itself. All right, kind of looks promising. I kind of see that first term over here. That's good. Now plus the first function, which was negative 2x cubed y, multiplied by the derivative of the second function, and the derivative of the second function with respect to x will give us negative 2x y squared e to the negative x squared y squared. Nice. And this we should automatically see, or we should be able to see at this point in time, that both of these derivatives are exactly the same. In other words, Clairaut's theorem holds. Now, Clairaut's theorem holds even though we're not evaluating at a given ordered pair, we still get the exact same value for the derivatives because this initial function is continuous everywhere. If it's continuous everywhere, then it must be true for all of the points on those domain, or on its domain, that Clairaut's theorem will hold. Therefore, Clairaut's theorem is now verified. Nice. Now, what if we wanted to mix higher order partial derivatives? So let's say that we wanted to find f sub x, y, z, and let's say x again, for this function, for f of x, y, z is equal to, let's say, z cubed, y squared, natural log of x. Let's see if we can find that partial derivative. So first we find partial of x. So partial with respect to x, that's going to be z cubed y squared over x. Then find that derivative using that function, find that derivative with respect to y. So finding that derivative with respect to y, that's now going to be 2z cubed y over x. Perfect. Now we want to take that function f sub x y, and we want to find the derivative with respect to z. Finding that derivative with respect to z, that's going to be 6z squared y divided by x. And then finally, we want to find that last derivative with respect to x. So taking this initial function that we found here, take that derivative with respect to x, that's going to be negative 6z squared y divided by x squared. And there you have it. This is the function that we wanted to observe for the partial derivatives, first with respect to x, then y, then z, then x. This is our final answer. There we are. Perfect. All right. Now, for the last part. For the last part, what we're going to do is we're going to rely on implicit differentiation. From Calc 1. Now, what implicit differentiation is going to be based upon? Implicit differentiation is based upon a function or an equation that we cannot directly solve for the variable in question. All right. So an example of this would be that if we were asked to find the partial of, the partial of z with respect to x, and that's going to be if we were given a function of x cubed z squared minus 5x y to the fifth, z is equal to x squared plus y cubed. Notice in this function we cannot solve for z directly, and because we cannot solve for z directly, it's going to create a whole big mess to try to find the partial derivative of z with respect to x. But we can do it. We can use implicit differentiation to go through and find that derivative implicitly. So there's a few things that we're going to have to assume here. All right, let's see if we can write this in a different color. I'm going to try purple here. So I'm going to assume that z is equal to some function of xy because I'm being asked to take the derivative with respect to x. All right. That means that any z variable must contain the variable x and y. X and y are independent of one another. Are independent variables, which means x does not depend on y and y does not depend on x. So when we take those derivatives, we don't have to account for that implicit differentiation using x or y. It's only going to come down to the z variable that we need that implicit differentiation for. So let's take that derivative now. The derivative with respect to x, I'm going to do this for the left-hand side, x cubed z squared minus 5x y to the fifth z is equal to the partial derivative with respect to x for x squared plus y cubed. Now, working through this using the derivative properties, I'm going to have x cubed z squared, that first derivative, minus the partial derivative for x, and that's going to be for 5x y to the fifth z is equal to the partial of x squared with respect to x plus the partial with respect to x for y cubed. So the first derivative here, or the first term on the left-hand side. The first term on the left-hand side, again, be very careful that we have a z and we have an x. And remember, a z contains the variable x. by our assumption up here. So we have to use a product rule here. So let's use a product rule. Using the product rule here, we're going to get the derivative of x cubed. Derivative of x cubed, that's going to be 3x squared multiplied by z squared. And then we need plus the first function, that's x cubed, multiplied by the derivative of the second. And the derivative of the second is going to be 2z multiplied by the partial of z with respect to x. And again, what I'm using here is the chain rule with that implicit differentiation. So here and here was the product rule. So that was a product rule. And this piece right in here was the chain rule. All right. Now, let's go through the second piece. Minus, second term. So that's minus, and then minus because that's a minus here. So the partial derivative here with respect to x, again, I have a variable x and I have a variable z. Y is a constant, remember. So I need the derivative of the first function. That's going to be 5y to the 5th multiplied by z. Then that's going to be plus, or let's say minus in this case, that way I don't have to carry the minus again. So minus the first function, which is 5xy to the 5th, multiplied by the derivative of the second function. The derivative of the second function is just partial of z with respect to x. There we are. All right. So then that part here, this part here, was this part here, and again we used the product rule. Now for the right hand side of the equation, partial of x squared with respect to x, that's going to be just 2x, and then the partial of y cubed with respect to x, that's a constant, so that means that's going to be a constant, and that goes to 0. Nice. So let's see if we can simplify this just a little bit more. So we have 3x squared, that's z squared, plus, let's multiply these here, 2x cubed z, and that's multiplied by the partial of z with respect to x, minus 5y to the 5th z minus, and this is going to be 5xy to the 5th, and that's multiplied by the partial of z with respect to x, with respect to x is equal to 2x. Now we need to solve for the partial of z with respect to x, because again, that's what we're looking for at the end. So let's get everything to one side that contains a partial derivative. So 2x cubed z multiplied by the partial of z with respect to x, and then minus 5xy to the 5th times the partial of z with respect to x is equal to 2x minus 3x squared z squared plus 5y to the 5th z. All right. Now that we have this on the left-hand side, we can now factor the partial of z with respect to x, which will leave us 2x cubed z minus 5xy to the 5th is equal to 2x minus 3x squared z squared plus 5y to the 5th z, which means at the end of the day we can divide by the left side, which means the partial of z with respect to x is equal to 2x minus 3x squared z squared plus 5y to the 5th z, all divided by 2x cubed z minus 5xy to the 5th. And there we are. There is our answer to this original question that said find the partial derivative. Now, even though we couldn't solve for z, we could still find its partial derivative. All right, we just have to use implicit differentiation. All right, so that's going to wrap up this section 14.3, and we're going to do sections 14.4 in just a little bit. So I'll wait to see you guys there.